Hello. This video is about another example of module computation. Here we will look at a specific module over what is effectively matrix algebra. That I'll use a coordinate-free version of it. So I'll start with a vector space over some base field K, and for all the discussion we can assume that this vector space is finite dimensional, and if we fix the dimension to be d, then the vector space can be identified with the coordinate vector space of length d vectors. And my ring in question will be the ring of the algebra of endomorphisms. So they are linear endomorphisms of V, which is the same thing as linear operators. On V in linear algebra terms. And in this finite dimensional coordinate version, linear operators can be represented one-to-one way by matrices of size d, square matrices with coefficients in our scalar field K. So the first observation is that we have a natural pairing between endomorphisms and vectors, or matrices and vectors, and that is, in matrix form it is multiplication, in this coordinate-free form is just applying endomorphism to a vector and getting the answer for this endomorphism on this vector, which is a vector again. And it is straightforward, it is a good exercise to verify that this satisfies the axioms of module, so it makes V a module over this endomorphism algebra. So we will look into this module, we will observe a very special property of it, which is the following. It's sort of the transitivity of this seen as an action. So for any pair of vectors, let's make them non-zero. We should be able to find a linear operator transforming the first into the second. So there is phi, which has this property. And to verify it, let's use matrix intuition, let's use linear algebra intuition. So what we can do, we can think of U as the first vector in a basis, say number 1, and think of V as again the first vector in a different basis, number 2, and then define our operator phi, which we want to find to be the transition from basis 1 to basis 2. So this is a result of linear algebra that any two bases can be identified by linear operators. So any two bases, for any two bases there is a unique linear operator which transforms the first basis vector by vector into the second, and that will just give us our desired phi. So this fact, this transitivity of action can be rephrased in a statement that V is a simple module over this algebra of operators. What is to be simple for a module is to have only trivial submodules. So let's just argue let's assume that there is a submodule and assume that it is non-zero, so non-trivial in this smallest possible way. Well, then there is a vector in it which is non-zero, and then for any vector at all in the vector space, we have this, by the transitivity, we have this endomorphism which transforms our view here into this arbitrary V. So that means that applying all endomorphisms to U, we will have this V in it, but it is also in U, because U is stable under module structure under this application, and so we have anything at all in U, so U must be the whole thing. And back to the logic, so we're starting with a submodule, assuming that it is not zero, then it has to be everything, so that makes this module to have only trivial submodules. That makes it simple. And any simple module fits into the input of the Schur's lemma, which is about endomorphisms of these simple modules. So let's apply the Schur's lemma to this case. Let's really run the Schur's lemma in this case and compute the endomorphism ring of this module of V as a module over the endomorphisms. So let's unpack the definition. We are to examine additive maps on V, and they have to, well, commute with the action of our ring. So they have to satisfy this identity for all V's and for all M's. This identity for all M's is just saying that the two maps commute. So we are seeking maps which commute with every linear operator. Well, if we start with linear operators which are scalar, we will see that these maps which we want to commute with them will be linear over the real numbers, sorry, of the basic field we have. And then there will be just linear operators commuting with all other linear operators. This construction is called the center of the ring of linear operators. So we are identifying here the algebra of endomorphisms of our simple module with the center of the ring. And finally, let's remember that the center of the ring, which is the same as the center, say, of matrix algebra, is nothing but scalar operators. So it is isomorphic to a copy of our basic field. And of course it is a division algebra as predicted by Schur's lemma. So that is the final answer for the endomorphism computation. The endomorphism ring of this module is nothing but scalar operators, and as a ring it is isomorphic to the basic field. So that is it for this example. More to come about modules over matrix algebras.